My name is Brian Young, and I'm kind of retired, but I work full time on this year round. So it's like I work like anybody else. I just don't get paid. Let's see. Oop. The motivation for the work is in my career, I've always worked with 3D full wave electromagnetic simulators that produce frequency dependent scattering parameters. And those simulators and results are used in general microwave engineering. I've done a lot with it in high-speed digital signal integrity and antenna design. I'm sure there's lots of other fields where this sort of classic EM simulator is used commercially. The issue with these tools is that they're very expensive. The one I typically have used, the dominant industry tool, is about $35,000 per year to lease. So I've seen that hurt innovation. Suppose you're an engineer and you want to explore some ideas on your own. If you use the company's tool, then they own it. If you want to do it at home, you can't afford it. I've also seen startups struggle with funding. They would like to use the leading industry tools, but they can't afford it. So they, lots of cases of they just pirate the tool instead. And then also there's some business models that are impractical at very expensive licensing. One particular business model I'm interested in is cloud-based modeling services. To provide that, you would need thousands to tens of thousands to hundreds of thousands of licenses potentially simultaneously. And if you're paying, the reason is Maxwell's equations haven't changed. So we're not getting a lot, in my opinion, for that $35,000 a year, in the sense that you're doing the exact same thing the exact same way you're doing it 30 years ago. So my conclusion is that an open source alternative is needed. And so that is what I'm working on developing. So how is something like that possible? These tools have major development teams at the world's largest software development companies. The thing about it is everything that you need is available today as free and open source. All the building blocks are there. So to develop a tool, you just need to glue the pieces together. And so that is a manageable programming exercise for one person or a very small team. I'm trying to do it as one person. Okay, so you need the 2D solution in order to set up the boundary conditions for the 3D problem. So that's this work. After the 2D problem, after you have the ability to do the 2D problems, then you can set up and solve the 3D problem, and that's what I'm working on now. So visually, suppose you have a 3D space and you want to solve, in this particular example, the scattering from a 90-degree bend in a differential pair for high-speed digital signal integrity. You have the 3D space where you've drawn your problem, and to solve it, you have to apply the boundary conditions to all the external surfaces. For the sake of solving the scattering parameters, you need to peel off the 2D ports where the energies come and go. So in this particular example, there's a port 1 with a differential pair that matches up to the 3D mesh, and then a port 2. And the 3D problem solution goal would be to find the scattering parameters for the energy entering port 1, how much energy is reflected, and how much energy goes through to port 2. So the first step being to solve the 2D problem, you need the fields to apply to the boundary condition, and you need the propagation constant and the characteristic impedances. The propagation constants will relate to the phase of the scattering parameters, and the impedances are needed for normalization of the S parameters. A full-scale simulator. So in this example, well, the direction I chose to go is use FreeCAD to generate the geometries. FreeCAD can export a file that's importable by Gmesh to generate the mesh. Then you just need text editors to bring in setup information and bring all that information into the 2D simulator. The 2D simulator itself uses MFEM, the main topic here, and the 2D simulator is also using SLEPC to solve the eigenvalue problem. Once it's done solving, it produces a CSV file for output that you can take into, say, OpenOffice and make plots where whatever you'd like. And then the field outputs go to ParaView, and then you can look at field plots. So this is sort of the marketing slide for the 2D simulator. And the reason why I wanted to show this was not especially to show the features and capabilities, but to show how MFEM factors into what it takes to make this full capability 2D simulator. So certainly MFEM applies the advanced finite elements. So with the arbitrary higher order elements, you also get adaptive mesh refinement, which is implemented, and then parallel processing. Then on the capabilities, there are the field-based calculations. So to calculate the characteristic impedance involves calculations on the field. So MFEM is integral to that. Conductor losses, surface roughness losses, and field distributions. Once again, MFEM makes all that relatively straightforward. So it's safe to say that without MFEM, you don't really have much of a go at a simulator. Okay, here are some sample results just to show it in action. The coaxial waveguide. Here's an example using second order elements. You can reduce the size of the problem by applying perfect magnetic conductor boundary conditions to solve it quicker or to more accurate using second order elements. At the bottom is a WR90 rectangular waveguide. This example, just to show more interesting looking fields, is the cutoff TE11 mode. This one was computed with fourth order elements. Upper left, very common structure in electronic packaging is a strip line. So this is a example showing a strip line solution with an etch factor on the center conductor, so it's not a perfectly rectangular conductor. That one was done with fourth orders. Coupled microstrip lines, another very common packaging structure, just to mix it up, calculated with third order elements. The bottom example is a partially filled rectangular waveguide. And that one was not using adaptive mesh refinement because it was 6 order elements and the smoothness of the fields that's really not necessary. This is an example showing 1/2 of a differential pair. So it's the odd mode of the differential pair, and just showing the adaptive mesh refinement, showing the starting mesh as produced by Gmesh, and then after 20 iterations of the 2D solver, how the mesh refines near the trace and especially near the corners of the traces, where the field strength is varying very rapidly. The plot in the upper right just shows the convergence of the impedance and the propagation constant as the mesh iterations increase. And you can see a nice smooth convergence right here. Oh, fourth order elements. You can see from the field plots with 20 iterations and fourth order elements that the field lines are actually very, very smooth. This is one of the examples from an accuracy check. This is the partially filled rectangular waveguide. The advantage for that is there's an analytical solution where you just need to solve a transcendental equation. And what you can see is that in the lower right-hand plot, that as long as your wave small errors produce relatively large relative errors, the error is falling around a little better than 10 to the minus 12th. So to my understanding, you're really not going to get better than about 10 to the minus 12th, because that means it's only carrying 3 digits of significant precision is all that's left. So I think that with the MFEM finite elements, that I'm actually seeing accuracy really at the limit of numerical methods. So for the development of this project, I wanted to talk about some of the challenges that I had going through. MFEM is, first off, MFEM is either vector 2D or vector 3D. In doing an electromagnetic propagated wave problem, it's a 3D vector field, but it's restricted to a 2D plane. So it doesn't fit exactly into MFEM's structure. So it actually makes it a more interesting problem, but you have to work out how to get it to do the 3D vectors on the 2D plane. Mathematically, the 3D vector can be separated into a transverse field and a longitudinal field. And so one's in vector and one's in scalar. So the key then is just to get those into finite element spaces so that it can solve, and I'll cover that on the next slide. The other issue I had is that frequency domain solutions require complex numbers. And when I started development, we were at MFEM 4.3, and I haven't moved off that yet. But MFEM has a start at complex support, but I didn't use it in this work. Third issue I had, mesh derefinement is not supported. At least I couldn't figure out how to get it to work. I'd get an error message that it wasn't supported, and I never found a workaround. So I'm going without derefinement for now. And then I found, at least for me, a relatively steep learning curve. So I'll go through 3 of these to provide a little more detail. Handling the 3D vector in 2D, I'm just using a paper by Jin-Fa Lee, published in 1994. And you end up with a generalized eigenvalue problem in the tangential electric field and longitudinal electric field in the complex propagation constant squared. This is all a complex operation, but really what I wanted to do is point out that going back to this paper from 1994, all of the matrices that were needed are actually directly computable by MFEM integrators. So it's just a matter of looking at what was called for and then finding the match and then putting that in. So it was able to get it to solve the 3D problem on the 2D space by without having to do anything special with respect to the integrators. So the tangential field is calculated using net finite elements, and the EZ is on the 2D finite element space using L2 finite elements. Once the electric field is solved, the H field is similarly broken into tangential longitudinal components and solved from E using 2 direct linear solves. Then all the other calculations for the currents and voltages, power, impedance, and so on, they're generally solved, well, they're solved within using MFEM directly, where all the math is broken out into real and imaginary parts and separately calculated. Handling complex numbers, the most straightforward way I could found to do it was to do all the setup in C++ using real values in MFEM, then go to text files, then import those into C, where I would use complex SLEPC and PETC, so that the total compilation has PETC compiled for real with MFEM, and it's compiled for complex for the C program. Then when it's done solving, you go back to text files, import them back into the C++ program. That's kind of a tedious way to do it, but for a 2D problem, going in and out of files isn't very time consuming, so you don't really notice, and it is possible to make it completely transparent to the user. So, ultimately, that can probably be fixed and not have to go to files, but it's working well for now. Then on the steep learning curve, I just wanted to point out my thoughts along the way. There are a lot of examples and they're very well done. What I found, which is often, sort of normally happens when you look at examples, is you can see what the code says, but you don't see why the code says it. So I had difficulty working out intent. And a lot of the examples are outside of my area of physics. So I'm an engineer with electromagnetic training, but not a physics training. So what would be pretty good for, I think, a physicist, for an engineer, was pretty tough for me. A lot of the methods in Doxygen have no descriptions. So I would often find that I was having to poke around in the code to try to figure out what a particular method was doing. And here's my biggest thing as a suggestion, is general descriptions of basic ways to get things done without using specifically coded examples or terminology. So for example, in general, using general terms, how do you multiply two vector fields? Or how do you integrate a scalar over a cross section? I ended up getting that, but I got it the hard way, basically with emails from Lawrence Livermore. So thanks a lot for that help. I wouldn't have gotten it done without that. So this is an open source project. There is a website for it, and there's lots of documentation there, methodologies, accuracy reports, installation guides, user guides, lots of things. And there's a link to GitHub. The project is on GitHub. Just to give you an idea of the scale, the current implementation is about 27,000 lines of code. And it's intended to be a full-scale project. So there is a regression suite covering 27 cases, 21,000 individual tests for the cases compared to exact analytical results. There are not many analytical cases in electromagnetics to compare to, but basically the 4 available are used. 2 cases against the literature, comparing the propagation constant, impedance losses, and also field values across cross sections. So I believe it's a very comprehensive regression suite. And it also serves as an extensive set of worked examples should anybody want to dig into it. So in conclusion, I'm presenting a full wave 2D EM simulator that's very strongly based on MFEM finite elements. It's useful for designing transmission lines and waveguides, but there's a lot of 2D tools running around, so I don't expect a lot of use on that. The expected primary use is in solving 3D electromagnetic problems. So you got to have one to do the other. So this is the first step, even though the 2D simulator alone is useful. The highlights for this project is that high accuracy on a general full wave waveguide and transmission line problems are possible with MFEM finite elements. I'm sure that few people would doubt that, but this is another proof, proved it to me anyway. There's plenty of flexibility in MFEM to handle the 3D vector problem restricted to a 2D plane. I include some details on solving complex valued problems with the real valued MFEM. And then I gave a couple of suggestions on documentation strategy that could potentially help with the learning curve. And then one more slide. I wanted to thank Mark Stoll for all the emails and helps with the feedback and tips and hints and so on. I don't think I would have been able to get it done without his help. So big thanks to Mark. That's it.
Thank you, Brian. Maybe we'll have time for one small question while Christina, the next speaker, is getting ready, maybe.
I've got a quick one. So what's your timeline? You were mentioning that you were, you released this 2D solver and you're working on the 3D solver. What's your timeline on that?
Strangely enough, I think the 2D solver is harder than the 3D solver. So the 2D solver took 9 months, and I'm about 1 month into the 3D solver. So I'm hoping 6 months. It could easily be a year, though.